All right, so at this point, we've spent a lot of time introducing the concept of entropy, which would have been this new thermodynamic concept, um, combined with enthalpy, which was one that you would have discussed previously. These two are sort of combined into this expression for free energy, delta G, and delta G will help us predict whether or not a reaction occurs spontaneously. So given a chemical equation, we should be able to use our constants page to figure out what the delta G, delta H, and delta S of these reactions are, right? So in this case, my reaction is really this process of liquid water being converted to gaseous water, what we call boiling or vaporization. And if I go to my constants page here, I can look up for these two components, liquid water and gaseous water, and I can use this information to calculate those thermodynamic quantities, right? So looking at the delta G for this reaction specifically, these are the two values that I would pay attention to. And then going back here, remember what we want to have in mind when we're calculating these delta Gs for our reactions is the sum of the product side times that stoichiometric coefficient minus the sum of the reactant side times that stoichiometric coefficient, right? So similarly to when you're calculating equilibrium constants, you say to yourself, products over reactants. For this, you want to be chanting to yourself, products minus reactants. So plugging in those values in particular, the delta G of my product gaseous water was negative 228.6. Minus the delta G for my reactant side, the liquid water, which was 237.1. And this gives me a delta G of 8.5 kilojoules. And I can do the same thing for the enthalpy of the reaction, where I would get 44 kilojoules and 44.0 if I'm going to be good with sig figs. And the entropy of the reaction, 118.8, and this is in units of joules per Kelvin. Remember, that's one of the tricky bits about this table here, is that my units for my enthalpy and free energy are in kilojoules, but my entropy is in joules. And it's per mole on the table, but as soon as we multiply it by that stoichiometric coefficient, which is in this case just 1, right? Because there are ones out front here that we don't bother explicitly writing, that drops away. That inverse mole drops away. Okay, so taking a look at these values, let's make sure that we can say a few things about this reaction. According to this delta G, is this going to be spontaneous or non-spontaneous? Positive delta G means non-spontaneous. Okay. Furthermore, what a non-spontaneous delta G is really telling you is that it's actually going to be spontaneous in the reverse direction. So non-spontaneous is the same thing as saying spontaneous in the reverse direction. Okay, so it's not that chemical reactions, it's never going to be the case that from an thermodynamic standpoint, a reaction just like doesn't happen unless it's at equilibrium, in which case it's already sort of reached its equilibrium point. It's always going to go one way or the other unless delta G is 0. And conceptually, this might be a little bit weird, but remember, we're talking about thermodynamic processes. So really just comparing the energy of your reactant to the energy of your product, not how fast that reaction occurs. So it could be that a reaction is non-spontaneous or spontaneous in the reverse direction, and that could be kind of counterintuitive, but it's not necessarily something that will occur on any sort of a reasonable time scale, right? We talked about that idea of how diamonds will spontaneously convert to graphite, but it's such a long process. It's one that we don't even really have to consider. But from a thermodynamic standpoint, it is still a spontaneous process. Okay, so anyway, looking at that value of delta G, we better be able to determine that it is non-spontaneous, or in other words, spontaneous in the reverse direction. And remember, that's because of these delta G knots, means that we're at standard conditions. And thus far, what we've discussed about standard conditions is that is specifically at a temperature of 298 Kelvin or 25 degrees Celsius. The delta H of this reaction, I calculated the same way I did my delta G. Looking at this value, we should be able to determine whether this is an endothermic or exothermic reaction. In this case, it's a positive delta H, so it's endothermic, which makes sense because to go from liquid to gas, those liquid molecules have to absorb thermal energy. And is this process entropically favorable or unfavorable? According to the sign for delta S, this is entropically favorable. All right. And the universe likes positive entropy. That's good. Furthermore, we should be able to tell that just by looking at this chemical equation here. This is something that we talked a lot about when we introduced entropy. Just given a chemical equation, can you determine whether a process is entropically favorable or unfavorable? In this case, because we're going from the liquid state to the gas state, we're creating a more disordered product, which is entropically favorable. So both the chemical equation and that value of delta S point to the same thing, that this reaction should be entropically favorable. All right. As we said, we're going to talk a little bit more about these standard conditions because we've talked about a piece of it, but not the whole story. Okay. And so on the one hand, we know that water does not boil at 25 degrees Celsius. So the fact that this is non-spontaneous makes sense, right? But if we think about it, if we were to, say, have a cup of water and we spill a little bit on the kitchen table or something like that, okay, if you forget about it or something like that, you're going to come back the next day and that water is going to be gone. It's going to have evaporated, right? We know that this process of evaporation does occur spontaneously at room temperature. So how can that be the case that this is telling us that this reaction is non-spontaneous? But we know that, in fact, it does occur. If we were to spill a little bit of water on a surface right now and let it sit, over time, that water would evaporate. It would reach the gas phase. So how can both of those things be true at once? We've talked about standard conditions and how that meant a specific temperature. It's even more stringent than that. Standard conditions also implies a very specific set of concentrations for your reactants and products. In particular, all of the gases under standard conditions are at 1 atm, and all solutions have a concentration of 1 molar. So why does water evaporate spontaneously at room temperature? Because we're not, given a random room like the one I'm in now, the partial pressure of water in that room is nowhere near 1 atm. The total gas pressure in this room is 1 atm. If it was all water, I'd be in big trouble, right? So the reason why water will evaporate spontaneously is because normally in this room right here, I'm not at standard conditions. Because again, standard condition is a very specific set of conditions. Right. So because I'm not at that 1 atm of my water, of my gaseous water pressure, I can't actually just look at this delta G naught. I'm going to have to look at another quantity here. And we're going to talk about that here in a second. Okay. But importantly, worth noting that standard conditions are a very specific set of initial conditions. Right. And so we can update what our delta G is really telling us. Our delta G naught, rather, is really telling us is whether a reaction is spontaneous if you're starting it at standard conditions. Right. That tells me whether or not that reaction above is spontaneous if I were to start at a water pressure of at a water vapor pressure of 1 atm. Right? If the water vapor pressure, if the pressure of this gas was that high, then yes, all of a sudden at 25 degrees, it's going to spontaneously condense, go the other direction. But in our real world, in this room right now, that is nowhere near the pressure of water. And so that's why I would see spontaneous evaporation. Okay, so now we're going to have to talk about predicting whether or not a reaction occurs at non-standard conditions. All right, so we're going to take an example reaction here. The dinitrogen tetraoxide gas going to nitrogen dioxide gas. Okay. If we calculated the delta G naught for this reaction, that would tell us, so first of all, how would I do that? I would go to my constants page. I would look up the value for, it's actually right here, so let's grab this one first. We're going to look at just at the delta G. So my reactant is this 99.8. And my product is this one right here. It's already circled for me, the 51.3. All right, so going back here, I'm going to do products minus reactants, but I'm going to have to take this product and multiply it by its stoichiometric coefficient. So 2 times the 51.3 minus my reactant, my 99.8. This would give me a delta G of 2.8 kilojoules, which is again telling me that this is non-spontaneous. But given what we've just learned, it's telling us it's non-spontaneous at a very specific set of conditions. Non-spontaneous when the pressure of the N2O4 is equal to the pressure of the nitrogen dioxide at 1 atm, right? That's what that delta G naught is able to tell me, is whether or not this reaction is spontaneous at this very specific set of conditions. I guess I can even add and 298K, right? Specific pressure and temperature conditions is what we mean by standard conditions, this little knot. All right. Okay. So two things that we're going to talk about here. First of all is just the relationship between the delta G of a reaction and its equilibrium constant, because these two are very very closely linked to one another. In fact, the delta G naught of a reaction is equal to negative RT times the natural log of its equilibrium constant. These will be values that would be given to you on your constants page, but R is actually that ideal gas law, 8.314, and it's joules per mole Kelvin. And remember, when we talk about delta G, we're talking in terms of kilojoules. So we're going to need to convert that by dividing R by 1,000. And temperature, in this case, at these specific conditions, first of all, temperature has to be in Kelvin. But for delta G naught, I'm specifically talking about that standard condition of 298 Kelvin. So this would be how we would solve for delta G if we had the K. But now the delta G is the easy thing to find, right? We can always use our table to get our delta G naught. So what we're going to do is flip this reaction, figure out the inverse, and that would be the KEQ, the equilibrium constant, is equal to E times negative delta G naught over RT. Right, so given a reaction here, we can figure out what the equilibrium constant is, right? We can look at our table to calculate delta G, and then we can figure out what our equilibrium constant is using that equation there. Okay, and so in this case, if I plug this in, I would get my KEQ is equal to a value plugging in RT. So actually, just to be clear, just to see here, this is going to be negative 2.8 divided by 8.314, but I have to convert that to kilojoules, right? This value here is in kilojoules. I got to convert my R to kilojoules times 298, right? And so what we should get is 0.323. So that's my equilibrium constant for this reaction, which if I'm looking at these, this makes sense, right? Both this and this is telling me that this is a reaction that favors the reactants, right? K less than 1 is a reaction that favors your reactants versus K greater than 1 is a reaction that favors your products. And this reaction here this delta G here telling me that this is non-spontaneous means it's spontaneous in the reverse direction, okay? But again, that's under this very specific set of conditions where the pressure of each gas is 1 atm. So now how can we tell if a reaction is spontaneous or non-spontaneous at non-standard conditions? We need to take a look at delta G, full stop, like no knot on it, just the delta G. And the delta G is equal to that delta G naught of a reaction plus RT natural log of Q. All right, so this is going to be an important equation here. Let's pick this apart. This is the delta G at standard conditions. Right, so it would tell me my spontaneous or non-spontaneous at that very specific set of conditions. This one right here will tell me if it's spontaneous or non-spontaneous at any conditions, spontaneous or non-spontaneous at any conditions, right? So non-standard conditions. And how does that work? Because of this term here, which is the value of your equilibrium expression outside of equilibrium. Right? That's what Q is. So what the heck do I mean by that? The value of your equilibrium expression outside of equilibrium. Well, let's just build our equilibrium expression for this reaction right here. Okay, KEQ, that was supposed to be a Q. Remember, we're going to do products over reactants. So I'm going to take the concentration of that nitrogen dioxide. I'm going to square it because there's this 2 in my balanced chemical equation, divided by the concentration of reactant. Okay. And one of the things that I hope you would have learned in your discussion of equilibrium constants is this idea that we could absolutely define our equilibrium constant for this reaction in this way. But for gases, something that's far easier to measure than concentration is pressure. And pressure is proportional to concentration. So what we're going to do is we're going to take this expression and substitute in the pressure values squared over the pressure of N2O4. Right, so here's my equilibrium expression here. I'm actually going to get rid of this one so we don't confuse ourselves. Here's this equilibrium expression. And if my reaction was at equilibrium and I punched in those pressure values, I would get that constant value here, right? That's why we call it an equilibrium constant. That would be if I took this expression and punched in the pressures of those gases when the reaction had reached equilibrium. If I'm going to punch in pressures of anything other than equilibrium, we're not going to call it K anymore. We call it Q. So Q is if I take this exact same expression, but I punch in these values that I would get outside of equilibrium. Okay, and so that's what we're going to do. We're going to figure out whether or not this reaction is spontaneous if we start out with a partial pressure of our reactant at, let's say, 2 atm, and the partial pressure of our product at just 0.5 atm, right? So I know that this reaction is going to want to go the other direction if both of these gases are at 1 atm. So now what I'm going to do is say, all right, well, let me sort of think Le Chatelier's principle here. What if I have this at a higher pressure? So this will be 2 atm, and this is a lower pressure. Does that still want to go in the reverse direction? Or under these conditions, will the reaction be spontaneous in that forward direction? That's what I can figure out using this equation here. Okay, along with my expression for Q. All right, so I'm going to need some more room. So let's... Here's my reaction. Oops, that's not what I want to show you. Here's our expression for the delta G. This will tell us whether or not the reaction is spontaneous at our non-standard conditions. We're going to need to use that expression for Q, and we're going to use these combined to figure out whether or not our reaction is spontaneous at these conditions here, right? So not standard conditions, this would be non-standard conditions. All right, and then we'll also need this delta G naught that we calculated. Okay, so now I'm going to take my Q expression, okay? But I'm going to plug in these specific pressures that I'm talking about here. So now the pressure of this gas is the 0.50 squared divided by that initial pressure of my reactant, the 2.0. So then my Q here would be, should probably do it real quick, 0.125, that's the Q. So now the delta G is going to equal that delta G naught, my 2.8 kilojoules, plus R, 8.314, but I got to divide it by 1,000 to sync up my units, times my standard temperature, the 298, times the natural log of that 0.125. Okay. And if we punch this in, we see that delta G is negative 2.35 kilojoules. And so this would be spontaneous. Spontaneous at our initial pressure of our product of just 0.50 atm and our initial pressure of our reactant at 2 atm. Okay, so what did we just sort of use this to show here? Again, we can use this expression here to figure out whether a reaction is spontaneous or non-spontaneous at any set of conditions. This delta G naught that we figured out tells us whether or not our reaction is spontaneous or non-spontaneous under one specific set of conditions, what we call the standard conditions, right? If we want to figure it out for anything other than standard conditions, then we need to use this equation here. Right? So the bottom line is delta G naught is not really the most helpful thing in the world for determining whether or not a reaction is spontaneous or non-spontaneous, because the vast majority of reactions are going to be carried out at non-standard conditions, right? So delta G naught just tells you one thing, whether or not it's spontaneous at standard conditions. If you want to know whether it's spontaneous or non-spontaneous at any other set of conditions, that's when you use this equation here. All right. And so just to kind of summarize what we sort of learned here, make some room. We said if the pressure of N2O4 was equal to the pressure of NO2 was 1 atm, then the reaction will go towards the reactants, right? Non-spontaneous, meaning it's going to be spontaneous in the reverse direction. But if the pressure of the N2O4 is 2 atm, and the pressure of the NO2 is that 0.5 atm, then the reaction, will go towards the products. And in order to show that, we had to use this equation here. Delta G of our reaction at non-standard conditions. All right, cool.